equations of kinematics in 2 dimensions. So before we dealt with the variable terms, but now we're going to deal with the actual motion. So here we learned that motion can be split into 2 parts: motion in the x direction horizontal, motion in the y direction vertical. So that's all we can break motion into. So think of motion as x and y separately. So when we're measuring a ball here, and let's say we throw it this way, we're not going to measure the parabolic curve. Instead, we're just going to measure the change in x and the change in y direction. So the motion in the x direction, the motion in the y direction. So let's extrapolate this even further. Let's go over notations. So x is displacement, as everyone knows. Previously, they used r because that would be 2D displacement, but here we're only dealing with 1D or scalar components. Ax is acceleration in x direction. Vx is velocity in x direction. And Vox is initial velocity in x direction, which is pretty self-explanatory because anything with the zero, I don't know what this is called. It's not a oh no, it's a subscript. Initial velocity in x direction. So that's pretty self-explanatory, all these terms. So these are the terms we'll be using here. These equations remain the exact same if we break the kinematic equations into 2 things. So let's go over the kinematic equations real quick. So VO, or sorry, the final velocity, or yeah, we'll just write that, which we haven't, but they don't use this terminology in the book. They just say V equals AT. So we can write this as a 2D kinematic equation, or in one direction, so like the x direction, as Vx equals Vox plus AT. So that's all the book wants us to do. In fact, we can do displacement as displacement equals x Vox t plus AT squared. And delta y would be the exact same thing, V0y plus, I guess it would be gt squared here because gravity is the y thing pulling it down, but it could be any acceleration downwards. So if we break the kinematic equation to 2 things, we can understand that. Now let's do an example here. Before we do, I just want to explain like a rocket ship, right? I'm not going to draw it actually because I suck at drawing. So we can, if there's 2 thrusters, so we'll do 1 thruster up, 1 thruster here, 1 thruster here, and not 1 thruster downwards because I guess we could use the force of gravity to pull the spaceship back down. So, and you never really see a spaceship with a thruster at the top. So we can measure this. So if we turn this thruster on, we can only measure the velocity and acceleration in this direction. And then if we turn this one on, we can measure in that direction. So if the bottom thruster is on, it's going up, and if the left thruster is on, it's going right. So that's what the curve will look like. Simply put, we can isolate all 2D kinematic movements into x and y movements, which we've already explained before. So here we have the x components of a crash velocity. So it's going to be the side components again. And acceleration are 22 meters per second and 24 meters per second squared. Or sorry, its initial velocity is 22 meters per second and 24 meters / second squared. So that means initially it's 22 meters per second squared, or 22 meters per second, which is the Vox, or the velocity in the x direction. We have 24 meters divided by second squared in the acceleration x direction. We don't have an initial acceleration because we don't deal with jerk in this book, I don't think. So, and jerk is just the derivative of acceleration, or the slope of acceleration, pretty much, same thing. The corresponding y components are 14 meters / second. So 14 meters / second is the velocity upwards. And note that we're using positive signage here because we're going upwards. You could still denote upwards as a negative sign component, but usually it's always going to be positive because people correlate it to math. So if we're going upwards, it's going to be a positive sign convention. And then we'll do 12 meters / second squared because that's what the book gave us as acceleration in the y direction. So Find the spacecraft's final velocity at a t equals 7. So what we're going to do is we're going to draw these vectors out. So here, I'm not even going to use the Cartesian coordinate plane because I don't want it to mess anything up. So here we have 22 meters per second. Sorry, my voice is a little raspy. Okay. And we're going to use the kinematic equation. Vx equals Vox plus AT. So the Vox is 22 meters per second plus 24 times the t, which is 7 seconds here. So this is after 7 seconds what our velocity vectors in the x and y direction will look like. So 14 meters per second plus 12 times 7. I'm going to use my mental math because I'm good at that. So we have 84 plus 14, which is 84 plus 14, which is 96. Wait, 84, 98. Sorry. I think my math is wrong here. So that's 84. 84. Wait, sorry. 70 plus 14, which is 84, and then plus another 12, which is going to be, wait, plus another 14. 98. Sorry, I don't know. My brain couldn't do that. And then we'll do 7 times 24, which is 168 plus 22, which is just going to be 190. So 190. So now we have, at the final moment, we'll have 190 meters per second at 7 seconds. And it's traveling upwards at 98 meters per second at 7 seconds. Now we just calculate the hypotenuse. Everyone knows we just used the Pythagorean theorem. So we get 213. And we'll do sig figs as well. So let's see. Honestly, I probably didn't write it with the sig figs, so we'll just do 3 sig figs because the book probably gave us it in 0.0, but I didn't write that down because I was not focused on that. And then we have 98 divided by 190, and we'll use the inverse tangent function here to calculate the angle. And what do we get? We get 27.28 degrees, and we'll just do 360 again, so 27.3 degrees. So 214 meters per second and 27.3 degrees second. Oh, they actually did 2 sig figs, so I guess I was right, but everything else was correct. And that is your example there. The answer is 214 meters per second at 27.3 degrees northwards of the x-axis. So